Hello, this is the review for the Pre-Calculus Honors Unit 6 assessment that will be on Tuesday. So, I hope you'll all watch this. The first thing you have to do is to be able to recreate the unit circle. And if I were you, and I was doing this, the first thing I would do is just start putting in things I know. Like I know the x-axis to the right is going to be 0, and you just got to figure out where you're going to put the degrees and the pi. That's going to be 0, and that's going to be 90 degrees. And we know this, and this is going to be 180 degrees, and this is going to be 270 degrees, right? That's what we know for sure. Everybody can remember that. Now, we got to remember that for the unit circle, remember the circumference of a circle, C, circumference equals 2 pi radians. 2 pi, the radius, and a radian is the radius, one radius length around the circle. So roughly that, not exactly that. Don't worry about that. You don't need that. Oh, undo. Can I undo? Right. Okay. So anyway, back to here. So that's 0, 0, 90 degrees, 180 degrees, 270 degrees. And the circumference is 2 pi times the radius. So if 2 pi gets you all the way around, so that's going to be 360 degrees, right? And that's going to be 2 pi radians. So if that's 2 pi all the way around, then this is pi radians, right? And if 180 is pi, then 90 is pi over 2. That's the same thing as 1/2 pi. And then 270 is 3 pi over 2, which, there we go, like that. And really, you should stop this and try and do it ahead of me, or maybe do it along with me, and then stop it and try and do it again. Something like that. I don't know, however you're good at memorizing, however it works out for you to memorize things is fine. So we got 0, 90, 180, 270. Now let's cut that in half again. And we'll go for our 45-degree angles, which are halfway between 90, right? So they're going to be this one, and then this one, and then this one, and then this, oh, not that one. Not that one. Okay, there we go. This one. And I left a little bit there, didn't I? Okay. All right, so 360, so 0, and then 45 is half of 90, right? 45, 90, and 45 is 135, right? And 180 and 45, that's because that's 45 degrees between 90, right? So that's going to be 225 right there. And 270 and 45 is going to be 7 and 4 is 11, so that's going to be 315, right? 315 degrees. All right, so now we're going to do those in pi instead, right? So we've got 0, 1/2 pi is 90 degrees, pi is 180. If pi is 90, if pi over 2 is 90, then 1/2 of that. If 1/2 pi is 90, 1/4 pi is 45, right? So that's pi over 4. And so that's 1/4 pi, and then 2/4 pi is 90, so 135 is going to be 3/4 pi. We're going to put 3 pi over 4 there. And then pi, and then 225, it's going to be 5 pi over 4. And then 6 pi over 4 is 3 pi over 2, that's 270. And 7 pi, I really wish this thing was thinner, over 4 is 315. There, okay. So now we've done all the quarters, right? Well, eighths, really. Eighths, they're quarters of pi, or eighths of the whole circle. So now we got to do the ones that are multiples of 30. 30 degrees, right? So that's gonna be, so the first one's gonna be 30 degrees right there. And then it's 45, and this one's gonna be 60 degrees right there. So I'll just color code those, right? So 30, 60, 90. So we're dividing pi into sixths with the 30 degrees. 30, 60, 90, 120 degrees. That's that one. 150 degrees. That's that one. 180 and 30 is 210 degrees. That's that one. And 210 and 30 is 240. And do we know we're on the right track? Yes, we do, because 240 and 30 is 270. And 270 and 30 is 300, right? 300 degrees, so that's that one. And then 330 is 330. 330 degrees. So I know most of you know this, or you're going to memorize or whatever. I just think going through building it is really, really important. Okay, so now if pi is 180 degrees, right? And the 30 degrees divide 180 into 6. 180 divided by 30 is 6. So these are sixths of pi going all the way around. So this is 1/6 pi, so that's just going to be pi over 6. 60 degrees is going to be 2 pi over 6, which is the same as pi over 3, right? And then we got pi over 2, that's going to be 4, that's going to be 3 pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6. So 120 is going to be 4/6 toward pi, right? So that's going to be 2 pi over 3. So that's 4/6 pi and 5/6 pi. That can't be reduced. So we'll go 5 pi over 6. 6/6 pi is pi. This is going to be 7/6 pi over here. 7 pi over 6. And then 8/6 pi. 8 over 6 is 4 over 3, so that's 4/3 pi. And I know I just switched the way I was writing it. I was doing 4 pi over 3, and now I'm doing 4/3 pi, but it's the same thing. So that's 8/6. 9/6 is 3 over 2. 10/6 pi is the same as what? 5 over 3 pi, right? That equals 5 over 3 pi, or 5/3 pi. And 10/6, so this last one, 12/6 is going to be 2 pi. So the one right before it has to be 11 pi over 6, or 11/6 pi. All right, so now we got all those, and now we really only need to know 3 numbers from here on out. I'm gonna let me switch colors here. We're gonna go ahead and put the x and y coordinates on the axes. So right here on the x-axis going right, the coordinates are going to be 1 for the x and 0 for the y, right? And then up here at 90 degrees, it's going to be 0 for the x and 1 for the y. And over here on the left, starting at the middle and going this way, that's going to be -1 for the x and 0 for the y. And then at the bottom, it's going to be 0 for the x and -1 for the y, right? So let's do our 45-degree triangle. So, and I know I did this in class, but I'm just going to do it again. So we know a 45-degree angle triangle is 1, 1, and square root of 2. But we know we can't have square root of 2. The hypotenuse has to equal 1. because we're making our right triangles on the unit circle where the hypotenuse has to be 1, right? So we have to divide that by itself to turn that into a 1, but then we have to do the same thing to the others to keep the proportions, right? And just as a reminder, 1 over square root of 2, some people and systems don't like radicals on the bottom. So if you multiply this whole thing times square root of 2 over the square root of 2, then you're going to get rid of the radical on the bottom, and you'll just have square root of 2 over 2. And either one of those works. And you notice that for a 45-degree angle, they're both the same, aren't they? So that's 1 over the square root of 2 and 1 over the square root of 2. All right, so that's only one number you actually have to memorize, right? 45, 135, 225, 315. It's all going to be 1 over square root of 2. It's just going to change sign because each quadrant, right, has a different set of signs associated with it. In quadrant 1, everything here is going to be plus and plus, right? This is quadrant 1. In quadrant 2, the x-coordinate is over here is always going to be minus, and the y-coordinate is always going to be plus. In quadrant 3, down here, the x and the y-coordinates are both going to be negative, always. And in quadrant 4, the x-coordinate is always going to be plus, and the y-coordinate is always going to be minus. So we can go back, and we can take that 45, and we can say, okay, well, it's 1 over square root of 2, 1 over square root of 2. All we have to do is change the signs, right? So let's do that. In quadrant 2, it's going to be negative 1 over square root of 2, and then 1 over square root of 2. In quadrant 3, it's going to be negative 1 over square root of 2. Oh, negative 1 over square root of 2. And in quadrant 4, it's going to be, the x is going to be positive, 1 over square root of 2, and the y is going to be negative, negative 1 over square root of 2. All right, so that's that. And now we're going to do our 30, 60, 90 triangles. And the 30, 60, 90 triangle, the thing to keep in mind is that the 30-degree, the line on the unit circle of 30 degrees and 60 degrees, the point on the unit circle where the angle 30 degrees intersects the unit circle, however you want to say it, 30, 60, 90 is going to be the same proportions on both of them. They're just reversed, right? So let's take a little space right here. I guess that seems good. And well, this is a 30, 60, 90 triangle. And we know, we memorized, or maybe we haven't, I don't know, that's going to be 1, 2, and the square root of 3. But again, we need to change this, so keep the proportions, but change the scale of it so that it fits on the unit circle with the hypotenuse of 1, because the hypotenuse on the unit circle is 1. It always is. That's the point of the unit circle. So we take that hypotenuse and divide it by itself. 2 divided by 2, that's 1. But if we did it to that, then we also have to do the same thing to the other two sides to keep the proportions straight. So now we can see that for every 30, 60, 90 triangle, this is the longer side, and you can even just visually verify that. The longer side is going to be square root of 3 over 2, and the short side is going to be 1/2. So let's get approximately the same color here. All right, so we got our 30 degrees, 30, 60, 90. The x-coordinate is the long one, right? So that's square root of 3 over 2. And the y-coordinate is the short one. So that's 1/2. Now, if we go up to 60 degrees, we can see the x-coordinate is the short one, right? If I make a little triangle like this, and I don't want to do it too much. I guess I can do it like that. So that's the 30, 60, 90 up to there, right? So now we can see that the x-coordinate is a short one and the y-coordinate is the long one, right? So the x-coordinate is going to be 1/2 and the y-coordinate is going to be the square root of 3 over 2. And now that's all we have to do is go around filling it in and putting the appropriate numbers where they go. So let's start with our 30-degree triangle and go over. So what we're looking at now is we're like flipping it over different axes and noticing things. So let's take this, just take this 30-degree triangle right here, and we're going to flip it over to here. And what's going to happen? The x-axis is going to be the same length, but it's going to be the opposite sign, right? So then over here, it's going to be negative, because that's the long axis, square root of 3 over 2, but the y is still positive, right? Now let's flip it down over the x-axis, the horizontal axis, and what's going to happen down here? Well, the x component is still the long one, so that's going to be square root of 3 over 2, but it's negative. But now y is also negative, right? And completing this little exercise on that, we'll go over here and look at the last of the 30, 60, 90s, where there's a 30-degree interior angle at the center there. And we'll notice the long x is positive, so that's square root of 3 over 2, and the y is negative, so that's negative 1/2. All right. So now what happens up here on the upper left in quadrant 2, where we have the 30, 60, 90, where the x is the 30, where the x is the short leg, and the y is the long leg. Well, we're just going to switch the numbers, but the signs have to stay the same, right? So the short leg is 1/2, so that's going to be negative 1/2, and that's going to be square root of 3 over 2, because the y component is the long one, right? All right, now we're going to go down here and in quadrant 3, and notice again, for our 240-degree, the coordinates for the 240-degree angle, the x-coordinate is the short one and the y-coordinate is the long one. So you'll notice those are just reversed, right? So now we're going to have negative 1/2 for the x and negative square root of 3 over 2 for the y. And then we're going to go around here to 300, and it's just going to be the coordinates for the 330. Keep the signs the same with respect to the x and the y, but flip the numbers, because the x is going to be the short one, and it's going to be positive down here, and the y is going to be the long one, but it's going to be negative in this position. So I think there's nothing more to say about the unit circle than that. And wow, when I stand back and look at it, it looks like a lot. But we built it very simply, very straightforwardly. And you can either try and memorize it, or you can just learn how to build it. Either way, it goes really fast once you kind of get it going. All right? So that is that. And now we're going to go to the next slide. And there we go. I guess I got to erase everything now. But you can get to everything, can't you? Hey, eraser. There we go. Okay. So you should be able to find sine, cosine, tangent, cosecant, secant, cotangent for any common angle in degrees or radians, right? So if I said, what's the sine? Oops, that's not going to do it. If I said, just the simplest one, like, right, what's the sine of 45 degrees? Well, the sine of 45 degrees is 1 over square root of 2. You would have seen that on the unit circle, which I encourage you to write out the entire thing. And remember that cosecant is the inverse of sine, secant is the inverse of cosine, and cotangent is the inverse of tangent. So if somebody said the sine of theta equals 4 over 7, then the cosecant, what is the cosecant? Well, it's just the inverse of sine, so all you would do is flip that fraction. So that would be 7 over 4. All right, and this is as good a time as any to put in here about solving triangles, although that might be the next one. I'm going to hit the... So that's pretty straightforward. You should be able to... Basically, this one is just talking about reading the unit circle chart and knowing that cosecant is the inverse of sine. So let's see. Okay, we'll just do them all here real quick. So we've got SOHCAHTOA, right? SOHCAHTOA. You can never write that too often. So sine equals the opposite over the hypotenuse. So this is for any triangle, right? We're talking about a triangle, a right triangle. And for an angle, the sine is going to be the opposite over the hypotenuse. The cosine is going to equal, that's the A, that's going to be the adjacent leg over the hypotenuse. The adjacent leg is the one that's actually touching the angle in question. Doesn't have to be the bottom angle, it's the angle in question, right? Whatever this cosine theta, whatever that angle is. And then tangent is going to equal the opposite over the adjacent. Obviously, if this is something that's super straightforward to you, you can fast forward the video. That's the wonder of it. So then we'll go cosecant is the opposite, the inverse, of sine. So that's going to be the hypotenuse over the opposite. Secant is the inverse of cosine. So that's going to be the hypotenuse over the adjacent leg, the one touching the angle. And then cotangent is going to be the inverse of tangent. So that's going to be the adjacent leg, the one touching the angle over the opposite leg, the one the angle opens up to facing. So, and all across the unit circle, you have all those numbers, right? Because every coordinate on the unit circle, you have a coordinate there, right? That is just your x over your y, because everything on the unit circle is a right triangle like that, right? So you got an x, if that's like the x-axis. You're going to have an x-coordinate and a y-coordinate, which, if I can remind you, because the hypotenuse is 1, that means the x-coordinate is whatever this angle is, say that's 30, right? So the x-coordinate is the cosine, and the y-coordinate is the sine of that angle. And then, of course, the tangent is going to be y over x of something on the unit circle. So if you're looking at your unit circle and someone says, well, what is the secant of 30 degrees? Well, the first thing you're going to start with is, well, secant is the inverse of cosine. Cosine is the x component. I know the x component of 30 degrees because 30 degrees is square root of 3 over 2 for the long leg and 1/2 for the short leg of that triangle, right? And so the cosine of 30 degrees, which is also the cosine of pi over 6, is square root of 3 over 2, which means the secant of 30 degrees equals 2 over the square root of 3. Okay? So it's really just getting super, super familiar with the relationships between all these trig functions. And I think that's enough for that screen. So I'm going to erase it now and move on to the next screen. What does this screen say to us? You should be able to convert between radians and degrees. And remember, the ratio of conversion is 180. Surprise, that's going to take you right back to that unit circle, right? You got your unit circle. You got 0, 90 degrees, 180 degrees, 270 degrees, right? That's all the way around the circle. And you know that all the way around the circle is 2 pi radians, right? Because the circumference of a circle equals 2 pi r. That's from a long time ago, middle school math. So 180 degrees, if it's 2 pi all the way around, this is pi. So 180 degrees is pi radians. So let's say you want to convert, something says let's convert 73 degrees to radians. Now usually when you convert to radians, they're going to be some multiple of pi. Not always, but pretty much, at least for now. It's going to be blank pi, 0.1 pi radian, whatever like that. Doesn't have to be, but it probably will be. So you are converting from degrees to radians. So you're going to take that little conversion rate right there. It's just 1, right? 1 in different units. That's what conversions always are. It's just a form of 1 with one type of unit on the top in the numerator and the other type of unit on the bottom in the denominator. We want radians, so we're going to put the radians on the top because it just makes it easier, and you'll see why in a moment. So here's our ratio, pi over 180. And we want to know how many radians that equals. We don't know, so that's going to be x. And that is 73 degrees right there. So pi over 180 equals x over 73 degrees. Oh, that should have a degree thing right there. Okay, so now that's, trivial algebra to solve, right? So you get 73 over 180 pi equals x. And typically, although like I said, not always, I'm not giving you a hard and fast rule, but typically on radians, you can just leave the pi there. So we just go 73 divided by 180, and that gives us 0.41 pi. 0.41 pi equals x. And does that make sense if we go back to the unit circle? Well, set 90, so this is going to be about 73 degrees is going to be about right there-ish, right? And if 90 degrees is pi over, that's half pi, so 0.5 pi, is this about 0.41 pi? Yes. Sort of just passes the is it reasonable test. So what if you needed to do, how about 0.84 pi? 0.84 pi, 0.84 pi radians to degrees. Well, we're just going to do the same thing. We're going to use our ratio, but we're going to put degrees on top this time instead of radians. So here's our 180 degrees over pi radians equals x degrees over 0.84 pi radians. Okay? And I know we got decimals on fractions and whatever, too bad. It works. So what are we going to do over here? We're going to multiply both sides by 0.84 pi, and we will get 0.84 pi times 180 over pi equals x, right? Okay, so from there, the pi's cancel out, obviously, and you're just left with 0.84 times 180, 0.84 times 180. So that's going to equal 151.2 degrees. Does that make sense? Well, let's see. 0.8, if 1 pi, which I should have used the same color the whole time, that's horrible. So if this is pi is 180, right? So 0.84 pi is going to be somewhere around like that. That's like 0.8 of pi, right? Something like that. And and this is 180 degrees, and we calculated about 151 degrees. So yeah, that definitely sort of passes the does it look reasonable test. So just to recap, here's how you're setting it up. Pi over 180 or 180 over pi. Either one, based on what you want. Now you can do it the other way. If you put the variable on the bottom, it still works. It just takes a little bit more algebra to get it there. So the thing you want to do is use this pi over 180 or 180 over pi, put the unknown on the top of the other fraction, and you're golden. So that is that. Next, if there is, for instance, an acute angle in standard position whose terminal side contains the 0.5 comma 3, you should be able to find, without a calculator, any of the 6 trig functions. Well, what do you think about that? It's not as hard as it sounds. Or maybe it doesn't even sound hard for you. And if it doesn't, well, I rejoice with you. So let's get a color here. I like that color. So there we have an acute angle in standard position. So what standard position means that whatever ray would go through that line starts at the origin of the coordinate plane. So there's our coordinate plane. And now we're going to go 5 in this direction and 3 in this direction, right? So we're going to get a point right there. And so that is an acute angle in standard position whose terminal side, well, if it's going to be the terminal side, I probably ought to erase this. It's not actually going to make any difference in what we do. But so that's an acute angle. The terminal side, it's in standard position, so it starts in the center. The terminal side is at 5 comma 3. So this is the angle we're thinking of right there. What is that? We'll call that A. Angle A. And they're going to ask what is the sine, cosine, tangent, cosecant, secant, or cotangent. So let's just do them all. So that's like the representation of what the question has. So what we're going to do from here is we're just going to go like this. We're going to take that line along with the x-axis and things, and we're going to make just a standalone triangle that is basically the same, right? So that's going to be 5, because that's the x distance, and that's going to be 3, and that's the y distance. And now the first thing we're going to want to do is calculate the hypotenuse. And how are we going to do that? Well, that's a simple matter of the Pythagorean theorem, right? So the Pythagorean theorem is a squared plus b squared equals c squared for a triangle, a right triangle like this, where a and b are the 2 legs and c is always the hypotenuse. That's the big deal. The Pythagorean theorem only works if c is always the hypotenuse. And so it works, you can have any variable you want, but you need to set the equation up so c is the hypotenuse. And so here we're going to do, we'll call, I'm just going to change colors a little bit there. We'll call this our A leg, and this our B leg, and this our C leg, right? So we're going to have 5 squared plus 3 squared equals h squared. Okay? So now we're going to take the square root of h and the square root of this. Got to square root both sides. And the square root of h squared, that is just going to be h, right? So the square root of 5 squared plus 3 squared. So that's going to be the square root of 5 squared is 25, and 3 squared is 9, right? So that's going to be 25 plus 9 is what? 34, right? 34. 5 times 5 is 25. 3 times 3 is 9. Yes, okay. So square root of 34 equals h. So now we know that this right here is the square root of 34. And now we can find all 6 functions with the greatest of ease. I'm just going to write SOHCAHTOA because you just can't write it too many times. So the sine equals the opposite over the hypotenuse. So the sine in this case is going to be 3 over the square root of 34. The cosine equals the adjacent over the hypotenuse. So that's going to equal 5 over the square root of 34. The tangent equals the opposite over the adjacent. So that's going to equal 3 over 5. The cosecant is the inverse of the sine. So that's going to be the hypotenuse over the opposite. So that's going to be the square root of 34 over 3. The secant is the inverse of the cosine. So that's going to be the hypotenuse over the adjacent. Let's see, square root of 34 over 5. And what else we got? Oh, the cotangent. The cotangent is the adjacent over the opposite, because it's the inverse of the tangent. So that's going to be the adjacent, which is 5. That's the one touching the angle, over 3. And there you go. How about that? All 6 functions. So here's the deal. Let me just recap for you. Whatever these two numbers are, whatever's in the coordinates, 5, 3, all you're going to do, you can put them on that, if you need to, draw the coordinate plane and put the thing in standard position, but you can also just think of those as the x and the y, or even if you want, the a and the b on a triangle like that. So that's your A and B and C, and that's going to be 5 and 3, whatever they are, right? Whatever they are. So that's pretty good. That's not too bad. I think that's pretty straightforward. And we're going to move on. Oh my goodness. I've been here a while already. I wonder how long it's going to take to upload this thing. Whew. Okay. You should be able to use the half angle, double angle, all those kind of things. I'm going to just do like 1 or 2 of those problems because we've been doing those problems for 2 days. And if you weren't paying attention in class, sooner or later, I'm just going to have to say, sorry, Charlie. All right, so let's do a problem here. We'll do this one. Well, I'll just write it out here. Let's say we've got it. We're given that cosine of x equals the square root of 3 over 2, and the sine of y equals the square root of 20 over 5. And they say, could you please find the cosine of x plus y? And you say, okay, I can do that. So what's the very first thing you're going to do? You're going to look at your reference sheet, because cosine x plus y is one of our trig identities. It's a sum identity because it's got a plus in it. So the very first thing you're going to do is write out the identity of cosine x plus y. On your sheet, it's a and b. Who cares if it's x or y, a and b? Variables are just buckets that hold value. So on our sheet, we have, and I'm going to use a and b because I like to just stay consistent with the sheet. So we're looking for cosine. So on our sheet, we have this. Cosine of a plus b, well, I hope I don't run out of room, equals the cosine of a times the cosine of b minus the sine of a times the sine of b. All right? So cosine a, cosine b minus the sine of a, sine of b. Alrighty. Now, of course, you notice I'm gonna change colors. That's what I'm gonna do to start with. So we're gonna call this one A and this one B, so that it matches our A's and B's on the formula. And unfortunately, we need we need the sine of A, and we need the cosine of B, which they haven't given us, so we got to solve these triangles, right? All right, so katoa, so katoa, we're going to need it. So we'll start with our A triangle here, our A angle, because that's just what we got to solve, right? So there's our A triangle right there, and the cosine is the adjacent over the hypotenuse. That's what this AHR. So it's the adjacent over the hypotenuse. So we know that's going to be square root of 3, and that's going to be 2. All right? So actually, that's a triangle that you might already know just by looking at it, I think. But we're going to solve it anyways. So what we're looking for is the y. I like to use y for the vertical one and x for the horizontal one when I'm doing my Pythagorean theorem solving, just to keep it clear. So when you know two sides of a right triangle, the Pythagorean theorem is always going to give you the third one. So let's see, adjacent over. Okay, so there we go. So what we know is that 2 squared equals the square root of 3 squared plus y squared. So then, just a tiny bit of algebra here, 2 squared minus the square root of 3 squared equals y squared. And now I'm just going to solve those numbers because they're small and easy. You know we're going to have to take the square root of whatever comes, right, to get that square of the y. So 2 squared is 4. Square root of 3 squared is 3. So 4 minus 3 equals y squared. So 1. Square root of 1 equals y. So 1 equals y. And you might have already seen that. If you were paying attention on the unit circle slide, you would know that. So that's already, we'll just do that. So that's going to be 1. And now we got to solve our other one, our B triangle. So let's just change colors to keep things pretty. So our B triangle, and we're just going to draw a triangle, right? It's a right triangle. And B says the sine of the angle is square root of 20 over 5. And sine is the opposite leg over the hypotenuse. So the opposite leg is square root of 20 over here. And 5 is the hypotenuse. And we need to find this angle in order to solve this whole problem. So here we go. So we're going to know, we know that 5 squared, that's the C, the hypotenuse, equals square root of 20 squared plus x squared, right? So now we're going to go 5 squared minus square root of 20 squared equals x squared. Well, that's going to be 25 minus the square root of 20 squared is 20 equals x squared. So 5 equals x squared. Take the square root of both sides and we end up with square root of 5 equals x. All right? So that's pretty good. All right, now we just have to go back. Why is there blue scribbling on the bottom over there? I don't know. There isn't any more. Now we're going to go back and we got to just plug in. So we've got all 3 sides of our A angle, all 3 sides of our B angle. So now we can just say equals, and what's the cosine of A? So we go over to A, and the cosine is the adjacent over the hypotenuse. So we'll put in the adjacent leg over the hypotenuse. And then cosine B, the adjacent leg. Oh, I didn't write that in. That is the square root of 5. The adjacent leg. I don't know why that's not sitting. So anyway, so the adjacent leg is square root of 5. That's the x component, right? Square root of 5 over 5. And then minus, and all I'm doing is transposing this formula and adding the values that we know. So then the sine of A is going to be the opposite over the hypotenuse. So that's going to be 1 over 2. And the sine of B is going to be the opposite over the hypotenuse. So that's going to be square root of 20 over 5. And this is going to be very messy at the end. All right, so you can see that it's going to have a common denominator, right? Because 2 times 5 and 2 times 5 on the bottom. So I'm just going to do that. 2 times 5 is 10. I can do that in my head. And then we're going to have square root of 3, square root of 5, minus 1 times the square root of 20. And that's not quite done, and I'll tell you why. The reason is because 20 has a factor that's a perfect square. So 3 and 5 are both, that could be square root of 3 times 5. It could be square root of 15, you could do that, or you can leave it square root of 3 over square root of 5. In fact, I'm just going to make it square root of 15 because I think it looks cleaner. Do you know what I did, by the way? For these kind of things, the square root of 3 times the square root of 5 also equals the square root of 3 times 5. So that also equals the square root of 15. So that's what was going on there. Now the square root of 20, let me just walk you through this, because some of this you just haven't done in a while, that's all. So the square root of 20, let's just go down over here. Square root of 20 equals the square root of 4 times 5 equals the square root of 4 times the square root of 5, and the square root of 4 we actually know, so that's going to be 2 square root of 5. We're trying to get this in the simplest form. All right, so now we go back to here, and so we got square root of 15 minus 2 square root of 5 over 10, and that's all we can do with that. There is nothing more we can do with that. So that, as they say, is that. Give me half a second here. Yep. Okay. So that's kind of how those things work, and I feel like I want to just do one more because let's see. I want to do one that is going to get hairier fractions in it, because you've got to be able to deal with hairy fractions. And we did them in class, but I'm just going to do one more now, and maybe we'll work a little bit quicker. Maybe we won't. So what we're going to say our given is, we have the cosine of y equals 8 over 9. Oh, this is actually a good one because it's half angle identity, and we only did like one of these in class. And the question is, what is the tangent of 1/2 y? Well, that's quite horrible, isn't it? All right, so if we know the cosine, we know the adjacent and the hypotenuse, but the tangent is the opposite over the adjacent. So what's the first thing we have to do? Same thing every time, we have to solve the triangle. So let's just solve this triangle. We don't need to label it because there's only one triangle over here. We don't need to label it like triangle A or something like that. Okay, so katoa, gotcha. So katoa, right? The cosine is the adjacent over the hypotenuse. So the adjacent is 8, and the hypotenuse is 9. And we're going to have to find this, right? So that's going to be the first thing we're going to do. Actually, I'll just keep the same color for that. So what that's going to make us do is go 9 squared equals 8 squared plus y squared. And then we're going to have to go 9 squared, and then we're going to subtract 8 squared from both sides equals y squared. And then we're going to take the square root of both sides. Square root of 9 squared minus 8 squared equals the square root of y squared is just y. All right, so now I have to get my calculator out to do that. So 9 squared minus 8 squared is 17. That's horrible, isn't it? 9 squared minus 8 squared is 17. So y is the square root of 17. Well, you can tell I'm making these problems up because the numbers are not coming out even, but I did do them before, so I'm not doing them on the fly, and I'm not going to make a bunch of mistakes, which, who wants to make mistakes? I don't want to make mistakes because I'm a teacher, and you don't want to make mistakes because you're taking a test soon. All right, so I did actually just violate one of my own rules, didn't I? I didn't write out what we were looking for, but I knew because it was asking about tangent that we were going to have to, well, actually I didn't know. So let's look at the formula sheet. Maybe I didn't need to do anything, but I'm pretty sure I did. So let's write it out. What is tangent of 1/2 y? So that's going to be one of these half angle identities. And there's a couple of them on there, and you can choose whichever one you want. So the tangent, and the question will probably say something like the positive value or the negative value or the possible values, or the question might even ask you about, it might give you a value. It might say for theta from pi over 2, it could say something like this to 3 pi over 2. So that would be in quadrants 2 and 3, right? So we're thinking of, here's our regular coordinates are going to be plus plus, right? And minus plus over here, and minus minus over here, and plus minus here, right? And remember, tangent is opposite over adjacent. So tangent is going to be positive where it's positive, positive, and tangent is going to be positive where it's negative, negative, right? Because it's one over the other. And then tangent's going to be negative here, and tangent's in quadrant 2, and tangent's going to be negative in quadrant 4 as well. I did not. There's 4, and there's 1. Okay, so there's all that. Okay, back to this. So the tangent 1/2 y, and the way they have it labeled on the sheet is x over 2. Same thing. Y, x, theta, whatever, doesn't matter. Equals, and this is the, oh, this one doesn't have the square root. Okay, that's all right. 1 minus cosine x over sine x. So that means we're going to get fractions over fractions, which is what I wanted, because then we could solve them together and just kind of rehearse how you do fractions over fractions. So that's what we're going to do now. So we know, we've done our little triangle, so we know what cosine x and sine x are. The cosine of the angle equals 8 over 9. So we know that right over here, we know that y, we know that equals the square root of 17, right? Because we calculated it down there. So I want to get a dark color here. So let's just do this in the middle here. So that's going to be 1 minus, and what's the cosine of the angle? The cosine is the adjacent over the hypotenuse. The adjacent, right, is the 8. The 8 over the 9. And then we're going to go over the sine of the angle, which is going to be the square root of 17 over 9. So we don't have to combine any fractions. In this particular instance, what we need to do, once you have a single fraction in the numerator and a single fraction in the denominator, then you try to get common denominators on both of them, and then the denominators disappear. So in this instance, what we're going to do is that 1, we're going to find an equivalent form of 1 that has a denominator of 9, which of course is 9 over 9. And then that's going to be minus 8 over 9. Hopefully you can see that that's equivalent, right, over square root of 17 over 9. So we'll just keep going. We can make that a common denominator, right? So 9 minus 8 over 9 over square root of 17 over 9. Now we have common denominators in the fractions that are in our main numerator and denominator. So those can be disappeared. And we're just about done, actually, right? Because 9 minus 8 is 1, and square root of 17 is what it is. So that's going to be 1 over the square root of 17. All right? So there's that. And I think that's pretty good. Should we do, let's see, should we do one more? You know, to be honest with you, I just can't even remember what's on the rest of this slideshow. So I might hop over to Delta Math at the end of this little party we're having and do one. But let's move on for this for now, because I want to get done and get home. All right, you should be able to solve for trig identities. For instance, if sine of theta, we've already done this like 10 times, like 10,000 million times. If sine of theta equals 3 over 7, what are the cosine and tangent of theta? We're just going to draw a triangle like that, and this is going to be our angle, right? And the sine, SOHCAHTOA, you can't write it too many times. Oh my goodness, and that's on tape. I'm sorry, everybody. It's the end of a long day, and maybe that gave you something to laugh at. I'm not going to go back and edit the video. All right. So the sine equals the opposite over the hypotenuse. So hopefully you recognize that as that. So that's going to be the opposite over the hypotenuse. So the sine is the opposite over the hypotenuse. And we're going to have to find that. Then we can find the tangent and cotangent. We already did this whole problem. I mean, I'll just set it up for you one more time. It's going to be 7 squared equals 3 squared plus x squared. So 7 squared minus 3 squared equals x squared. So the square root of 7 squared minus 3 squared equals x. I know I said I was just going to set it up for you, but it's really hard for me to stop. 7 squared minus 3 squared equals 40. So the square root of 40 equals x. And that can actually be broken down a little more. Might as well have some practice in simplification, right? So that's going to be square root of 10 times 4, right? So that's going to be square root of 10 times the square root of 4. And the square root of 4 is 2, so that's going to end up being 2 squared root of 10, right? Okay, good. There you go. That's x. That's all we did so far was solve for x. And then once you have that, you have the opposite of the adjacent, blah, blah, blah. There we go. All right, moving on. Let's see. You should be able to prove that cosine squared theta plus sine squared theta equals 1 if given a partially filled out thing. And I don't know what I did with my notes on that. I have notes on that. But I will tell you this. It's not hard. They give you the things that go in the blanks. It's like the same thing we already did, like, right? Addition property of equality, subtraction property, multiplication, division, that kind of thing, right? So I don't have anything for that, but you should be able to like walk that proof through. And next, all right, you should be able to solve trigonometric equations. This is the big daddy right here, and this one's a little bit tough. And this is the one that I hope. This problem right here is why I kept saying, watch the video, watch the video. Make sure you watch the video. All right, so here we go. It says to try to solve this thing for x, right? So here's what we're going to do. And I'm just going to walk you through it. And there's going to be just a couple little things. In fact, there's going to be one trick that's just, it's power. It's a power trick. And you're going to like it when you see it, I think. Or maybe you'll hate it when you see it. I don't know. But it's definitely a power trick. It's called U substitution. And U is just a variable. And the U is just by convention. You could use any variable you want. But you'll see what I'm talking about. But U substitution comes up in later math too. All right, so we got the cosine of 2x equals sine of x. Okay, so I'm just going to rewrite this like this. Oh, I need actual writing stuff. All right, so I'm going to rewrite it like this. The cosine of 2x plus the sine of x equals 0. So I've added sine x to both sides. So that's good, right? Now, here is something that you need to know. And is that? So cosine 2x has an identity. I don't know where you're going to find this. That is 1 minus 2 sine squared x. Cosine 2x is 1 minus sine squared 2x. Is that going to be, it's probably on the sheet. Cosine 2x is 1, it's on the sheet, okay? Take note. That equivalent is on the sheet. Cosine 2x equals 1 minus 2 sine squared x is an equivalent that's on your reference sheet. So nobody has to have memorized anything horrible or difficult. All right? So now we're just going to put this other part of it back in there. And the thing that triggered me wanting to do that is because if you can get it all into one function, that like changes everything. So now we're all in terms of sine x, right? Because sine squared x is just sine x times sine x, right? It's the same thing as saying, just to refresh your memory, it's the same thing as saying this. All right, so that's that. Now here's the thing. You're going to substitute a variable for sine x. So we've got sine x in 3 places, right? Because we've got a sine squared x and a sine x. So sine x is a value you can solve for. And if you can solve for the value of sine x, then you can go back in and actually replace that with sine x and get to where you need to be. So what we're going to do, and if this goes horribly, like on the test, it will only reflect on me in terms of the comparison with the counting, and I will not be counting it against you if this is a crash and burn. So basically what we're going to do is substitute u for sine x. So sine x is u, and sine squared x is u squared. And we're going to, and instead of trying to solve for the x right away, we're just going to solve for sine x. We're trying to find out what the value of sine x is. So let me rewrite this with that u. 1 minus 2u squared plus u. Okay, so now Now that should trigger something in your head, because if you rearrange those, what do you get? You get something in standard quadratic form, right? So you're going to get negative 2u squared plus u plus 1 and equals 0. And that is something you can solve, right? So we'll just do a little quadratic review. When you can get something into the formula a squared plus b, ax squared plus bx plus c equals 0, you can use the quadratic formula to solve it, and the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. And don't give up. Like, don't say, oh, forget it, I'm not going to bother with that one. Because you've done quadratic formula before. You've done everything. The only two things that are a little bit unusual here are recognized that cosine 2x has an identity that you can use, and substituting a variable u for the value sine x. That's the only thing different. You can do this. You can do this. All right. So in our formula, so we have, I'm just going to change a little bit of color so it's easier to sort of track a little, I guess. So here's our little formula here. It's going to be negative 2u squared. We're almost done, by the way. Plus u plus 1. So our a equals negative 2, and our b equals 1, and our c equals 1. Well, that's going to make the formula easier, isn't it? Yes, it is. So, change color again, just to make it easier to track along. All right, so now, we got our negative b, blah, 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 blah. So we're going to have negative 1 plus or minus the square root of b squared, that's 1 squared is 1, so I'm just going to put in 1 there, minus 4 times a, which is negative 2, times c, which is 1, right? Okay, so that's, all of a sudden this horrible thing just turned into like 1s and 2s, all over 2 times a, which is negative 2, right? All right. Almost there. So you crank out the math, and what you're going to find out is that's 4 times negative 2 is negative 8. And let's see. And that's negative, it's 1 minus negative 8, so it's going to be 1 plus 8, so that's going to be 9 underneath the parentheses, and square root of 9 is 3. So you're going to end up with negative 1 plus or minus 3 all over negative 4. And that's not too bad, right? That's not too bad. So that gives you 2 possible values for sine of x, right? Because that's what we just solved for. These are values of sine of x. So, and let's just get another. So sine of x, sine x equals, it's either going to be negative 1 minus 3, so it's going to be negative 4 over negative 4, which is 1, right? Or it's going to equal negative 1 plus 3, which is 2. So wait, hang on. I should have put a 1 there. Want to keep things clear? Keep things clear. Negative 4 over negative 4, that's 1. Okay. And the other possible value of sine is going to be negative 1 plus 3. So that's going to be 2 over negative 4, which is going to equal negative 1/2. All right. So those are the 2 possible values of sine. Now, the last piece of this is what values, so we have an interval here, and so what we want to do I'm gonna have to back to the unit circle. You can't escape it. So pi over 2. So it's going to be on the interval. This is 0, right? So we're going to go to pi over 2 to 2 pi. And 0 is 2 pi's all the way around, right? So we're looking for a value that is somewhere in there. Okay? So where are we going to find that? Well, pi over 2, what's that? That's 3.14 over 2. So pi over 2 is greater than 1. I'm making too much stuff there now. So we're gonna notice that our value of 1, this value here, 1, is going to be somewhere in quadrant 1, right? Because it's between 0 and 3.14 over 2, which is greater than 1. So that cannot be the answer. Sine is the y component, right? It's cosine, sine. And here we have sine is 1/2. So it's going to be somewhere down here, right? Because it's negative. So this has to be the answer and the only answer you can get. So let me recap. There's really nothing on the board right now that is super way out there. There's just a couple things you haven't really been exposed to or seen too much. The first one is back up here. So if you see something like this, you can notice that it's an identity. And if you're not sure, just look at your sheet, because you will have your sheet, right? And so we noticed that this was a sine identity. The cosine 2x, one of the equivalents had sine in it. So we chose that identity so that we were left with all sine x values. And once our variables were all sine x values, we substituted a variable for sine x just for the ease of solving the math. So we said, well, u is going to equal sine x. We will let this variable u equal sine x. And then we solved for u. And once we did that, it was easy to see that that's a quadratic, right? Because you got a variable squared and then a variable and then a constant equal to 0. So we went up and we redid we remembered our quadratic stuff, and we used the equation that we got from down on the lower left. We identified where our a, b, and c terms are. We entered them into the quadratic formula, and we got our possible 2 values out of the quadratic formula, because it's always 2 possible values, plus or minus, right? And those are the values of sine. So those are the possible values of sine that satisfy this equation. And we're working in radians because it's, 2 pi and all that stuff, right? So one value of sine turned out to be -4 over -4, which is 1. And 1 as a value of sine, because sine is the y coordinate, right? Here. Wait, I feel like I'm losing. I feel like I just lost something. Sine of x. Cosine, sine. Cosine, sine. Well, it could be over here too, right? Okay, so maybe there's two possible answers after all. I might have gone a little fast for you there. Let's see, too fast for me. If the sine of x is 1, it's positive there and there. So yeah, so either one of those would work. Okay. Yeah. Well, it was still a good illustration of mapping out the range, the limited range, the limited domain of the function to see which value or more would fit in there. And I'm going to move on because this thing is getting long. Okay, these are calculator ones. Given that sine of theta equals negative 0.7642 with the restriction that blah, 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 blah. Okay, so there's just a tiny little trick to this, and it is, in fact, a really tiny little trick because we just have to remember what sine and cosine are on the unit circle, right? If you're on the unit circle, and we'll just draw sine. Sine is negative, so it's going to be somewhere down here, right? Because it's the y-coordinate. And so we have a restriction, 3 pi over 2 and 2 pi. So this is, that's pi over 2 right there. That's pi. That's 3 pi over 2. And that's 2 pi over there, right? So that's our restriction. So now we know that whatever we're looking for, so we've identified where the sine is going to be negative, but now it's between 3 pi over 2, so the thing we're actually looking for has to be here, right? In quadrant 4. And who doesn't like writing the Roman numeral 4? So it's going to be somewhere over there. Now all we have to do is, don't kill me, it's the Pythagorean theorem, right? That's what it says, Pythagorean theorem. And so let's just draw some random triangle right here. And what do we know about that triangle? What do we know? We know that the sine, and remember, cosine, comma sine, we know the sine, we know the value of sine. We know the value of the y part of this, right? That's negative 0.7642. And it's going to always tell you to find something, with to a certain degree of precision, to 4 decimal places or whatever, right? So how are we going to find, and this is what we want to find. Well, is that possible even? Is that possible? Well, yeah, it is. Why? Because that's 1, right? And we know the Pythagorean theorem, which is a squared plus b squared equals c squared. So in our case, it's going to be x squared plus, and this is going to be weird, 0.7642 squared equals c squared. And what is c squared? What's the hypotenuse squared? It's just 1. Doesn't that make things easier? It sure does. Equals 1, right? All right. So the next thing would be to say x squared equals 1 minus negative 0.7642 squared. And whenever you got like negative squared and stuff like that, you just always got to try and visualize what you're actually looking for. So x squared equals 1 minus, on clear, 0.7642 squared. 1 minus 0.5840. So that's going to be 0.4153. 9, so that's going to be 4, 0.4160 is x squared. So x equals the square root of 0.4160. So the square root of 0.4160 equals 0.645. And that's your answer right there, right? Because that's what you're looking for, x, 0.6450. It's just the Pythagorean theorem, only you're doing it to the 10,000th place in your decimal, right? But that's all it is. And does that make sense? 0.7, 0.6, yeah, that seems roughly about right, just sort of visually. And now I really better get moving because, well, oh, I got one more. Got to do this one. Jim bought a large pumpkin pie with a 7-inch radius. He cut himself a piece with a central angle of 35 degrees. What is the perimeter of Jim's piece of pie? Round your answer to the nearest hundredth of an inch. All right, so this is simpler than it seems. This is one of those things that like you look at it and go, what? All right, so, but it's not so hard. Ready? Here we go. I even got orange. That was an accident, but I'll take it. And 7-inch radius, right? Okay. And a central angle of 35 degrees, because he's not selfish. He just wanted this much pie. All right, 35 degrees. What is the perimeter of Jim's piece of pie? So, what's the perimeter? The perimeter equals all the way around, right? All the way around. Okay, so we're gonna have, I guess that's my pie talk. We're gonna have some pie. So we got 7 there and 7 there, right? So we got, let's just put them over here. Okay, so we got 7 and we got 7, and then we still need this piece, right? How far is that? Well, goodness. We should just throw up our hands and walk away. Not. So that is 35 360ths, right? Because it's degrees. 35 360ths around the pie, right? So the only other question you have to answer now is how far is it all the way around this pie? Well, you happen to know that, I hope. The circumference of a pie is 2 pi r. So the circumference of this pie is going to be 2 pi times the radius of 7. So the circumference of this pie is going to be 2 times, where's my pi button? There it is, pi times 7. So the circumference of this pie is going to be 13 and 100th of an inch. So we better keep some precision here. Since they want the answer to the 100th, I'm going to keep 4 decimals just to make sure we're really as precise as we can be. 2 pi r radius 7, 13, 2 times 3 is 6 and 7. Wait, does that make sense? 2, oh, yeah, see, the gut check. The gut check is such an important little piece of mathematics because sometimes you punch the wrong button on your calculator or something, which I just did. I did 2 times pi plus 7. So 2 times pi times 7 equals, that's more like it, 43.9823. So that is the circumference. So now what we need to do is say, well, the only thing, I'm going to change colors again, I think. So, but we don't need the whole circumference, do we? We only need 35 360ths of it. So that's all we have to do. What does that equal? Well, let's see. 43.9823 times 35 divided, I hit equals there because I want to just make sure I don't have any order of operations problems, divided by 360 equals, that's not right. So 35 times, I think I didn't put the decimal point in, 982, because the number was huge. So 35 times that equals that, and we're going to divide that by 360. And there we go. So we got 4.2761. So if the whole pi is 43.9823 inches around, 35 360ths, because it's 360 degrees for the whole, and 35 is the piece, so that's the ratio, the percentage we got. That means that this distance right there is 4.2761. And now we just add that to the other two, 4.2761. And, well, the point's going to stay the same. So who cares about that? We'll just leave that. And 7 and 7 is 14, and 4 is 18. So that's the perimeter, because I know you're going to want to know that at some time. That's the perimeter of, that's not to the 100th. That's to the 10,000th. So the actual answer is 18.2, round that up, 8. 18.28 inches is the perimeter of Jim's piece of pumpkin pie. How about that? All right. I think that's it. The end. That's it. If you're with me, man, God bless you. I'm proud of you for being here. And I'm going to stop this thing. So I'll see you Tuesday. Bye-bye.